Okay, so we'll start once again. So what was discussed yesterday? We started with a little bit of neuroscience, mathematics, and then we touched upon the fundamentals of deep learning, right? Up to the feedback process, the loss function is what we discussed in yesterday's session. And we also discussed the steps in training of a neural network. We covered 5 steps, if you all remember. The last 6th step is what we plan to discuss today. So we stopped exactly at BCE, that is binary cross entropy. And do you remember where is it used? What kind of problems, what kind of problems do we use this binary cross entropy? Yes, classification problems. And what about regression problems? What are the loss functions which are associated with regression problems? Mean square error and mean absolute error. So do you think there are only 3 or 4 or 5 loss functions? There are many more, right? We discussed only superficially. We are starting with the basic stuff. But as we explore more of deep learning algorithms, other generative AI algorithms, we'll be discussing much complex loss functions as well. So coming to what we discussed yesterday, this was the neural network which I showed you in the PPT slide. And what we did yesterday was understanding how the input data flows, right from the input layer, covering all the other layers, and finally it reaches the prediction state. So we start with predictors, that is the X values, and the final output is a prediction, which is a Y value. So we understood the flow of data from left to right. So this is called forward propagation. Yesterday I did not use that keyword intentionally. I wanted to keep it as simple as possible. But this flow of data from input stage to the prediction stage is called forward propagation. So data flow from inputs to output in an ANN is what constitutes forward propagation. Now coming back to where we left off yesterday, up to step 5, the step 6 is also equally important. Now we are receiving the feedback from loss functions, but from the feedback, what exactly are we doing? We said that the neural network starts with the input data at a random state. It flows through several layers. It comes to the prediction state. Then we use a loss function to give a feedback to the neural network saying whether it's performing well or no. After that is what we did not discuss. Today we'll be focusing more on that. But how to correct the function is where we left off, right? And do you remember I categorically mentioned what changes and what doesn't change in a neural network? What is it? Parameters don't change? Okay, we'll start with this question. What doesn't change? Input, yes. The input data, the variables that we assign in the input layer, x1, x2, so on. If we consider that to be the input, then that doesn't change. The x values, let's remember it throughout the session that way. The x values, which we are using to initialize the input data, is what remains the same. We cannot change it because it is recorded data, it is historical data. Our neural network has to get trained on it. So we do not have flexibility in changing the input data. It remains same throughout. So what else can change? Weights and biases, right? Because these are the variables. We are initializing them randomly. So we have flexibility in that area. So we can change the weightage of each input depending on the loss function and the feedback that we receive in the end state. But how exactly can we change them? Can you just look at a loss function and decide how much weightage should each neuron get? Is it possible? Not really. And yesterday we also discussed that there has to be some kind of automated learning process, automated feedback, because everything cannot be done manually. A simple neural network of few layers might look easy, but it's not that easy to do all of this using a program which is dealing with each neuron one at a time. So this entire process of learning has to be automated somehow. So coming back to this question, how to correct the function? X values, they cannot be changed. Whereas weights and biases can be tweaked, meaning they can be changed. Depending on the feedback we receive, they can be modified. So we have flexibility in terms of weights and biases. So whenever we are saying that a neural network is getting trained or a neural network is learning from the data, it means it is changing these values, the weightage. How much weightage should it give to certain input? Should it give less weightage? Should it give more weightage? So that is what the neural network is essentially learning. But how do we decide how much does the weight or a bias change? That is exactly where the derivatives come into picture. You might be knowing what are differential equations, derivative functions, but do you understand what is exactly the purpose of using derivatives? To find the slope? But in a function, yeah, you're right. But in a function, how do you think that is going to help me?
The change of y with respect to x.
Correct. That is the essence of derivative. So y is my output function. X is the input that I give. So why should I know dy of dx? How much output changes? With respect to input. So how do you think we can attach this to neural network training? Correcting? Finding the errors? Reducing the errors. Yes, you're partially, all of you are giving me answers correctly. But let's do it in practice and see. So the main essence of derivatives is to know how much is my output value changing if I change something internally. So if y equal to f of x, y is the final output, f of x, x is the input. So if I change x slightly, reduce it or increase it, what is the impact it has on the output? That is y. So that is the main idea of using derivatives. And we will be using derivatives in neural networks for the same reason, but at a neuron level. Because remember, each neuron is a part of a math function that our neural network is building. A neural network is building a super complex math function where each neuron is contributing a bit, and then we arrive at a final solution. So derivatives, when we think of derivatives, we have to think of it at a neuron level. Then it will be easy for all of us to visualize what exactly is happening, right? So derivative, I've taken this definition from Wikipedia. It says it quantifies the sensitivity of change of a function's output with respect to its input. So whatever input I'm giving, the weights and biases, because that is what is going to change. They are the variables because they vary. So if I change my weights and biases in a certain layer, how is it impacting my output? That is exactly how I'm going to use derivatives for ANN training. So this is the picture again. Now if we look at the complete picture, how do you think we can derive the weights and biases? How do we know what changes have to be done? Because there are multiple weights, multiple biases, multiple activation functions, and each neuron is performing a simple math function. And you have n such different neurons in each layer. So it will be difficult to visualize. So let's go step by step. Let's hide this layer for some time. And whenever we say we have to correct the predictions of the layer, that means we have reached the end here on the right. We are now at the rightmost node. So now when we have to do the changes, we have to go from right to left. So earlier what we did was left to right. We moved forward in calculating some output using the randomness. But now, since we have a feedback thing here in place, we now have to move from right to left because we have to correct each and every step so that we arrive at a correct solution. So now we move backwards in a neural network. Now immediately what we get to see behind or just beside the prediction layer, we have the activation functions. So you don't have to look at the entire neural network to understand how weights and biases get updated. We can start one layer, one neuron at a time, and the same recursion principle applies here, right? Whenever you have a mega super problem, you chunk it down to smaller problems. You deal with the sub-problems, you solve all the sub-problems, the main problem gets solved. So is the case of ANN training also. It becomes difficult to visualize, so you can start small. You can look at the layer which is immediately before the prediction. So what is there? We have the activation functions, right? Because those are the ones which are feeding the final output. So derivative of an activation function is where we can start, because that is what is immediately connected to the final output y. So measure each neuron's and its activation contribution to the error. So whenever we are doing a derivative, we do a derivative at a neuron level. So we are checking how each neuron is contributing to the error finally. So we start again with the activation layer because that is immediately next to the prediction. And again, to reiterate, derivative tells how much the output is impacted when the internal variables are slightly changed. I'm just rephrasing my statement so that it becomes easy for you all to understand. Then we can decide and tweak the weights accordingly. So let's say I change one weight and I see that the error has increased further. That means a feedback is telling me I have to reduce the weightage. Then my error rate will decrease. So applies for all the neurons in the neural network. So one step at a time is how we can do, and one neuron at a time is how we can analyze to understand exactly how neural networks get trained. So same principle works for recursion here. Whatever we use for recursion, we can apply the same thing here. You solve a sub-problem, the main problem gets solved. So think of only one neuron in the entire neural network or one layer at a time. Then you can do the hyperparameter tuning accordingly. So we can simplify the earlier picture that we had in the previous slide. This was the complex picture. Making sense out of this and derivatives will become complex. So we'll take only a single neuron because we want to do it one neuron at a time. So let's do it for one neuron at a time. And this is how the picture looks, right? Where you have two inputs. The thing in the circle is a neuron. X1, X2 are the input data. They cannot be changed. Whereas W1, W2 are the weightage that we are giving to each input respectively. So we combine that data to calculate the value of Z, and then we pass it to the activation function Tanh. And why do we use activation function? Non-linearity. And why do we introduce non-linearity? What is the need? Louder, please. To solve multi-dimensional problems. Any other answers? We discussed a couple of other reasons why non-linearity is required. Providing a fit? Okay. To fit a suitable function for the data we have, right? So basically, I showed you with the help of data distributions yesterday that data distributions may not be very simple. They might be very complicated. The data distribution may not be sufficient. It's not possible to classify a data distribution using a single slant line or a straight line. So that's the reason why we have introduced non-linearity, so that the function fits well with the data that we are providing the neural network. So we start with this simple neuron to understand how derivatives can play out, how do we calculate the derivatives, then how do we decide the weightage, and how do we go about changing the values of weights and biases. Now to clarify again, x1, x2 are the input that we are giving. Z is the value which is a combination of w1, x1 plus w2, x2 plus b, and output, the final output is Tanh of that Z value. Right? So this is a single neuron. This has to be very clear in your mind. Now the activation function, do you think Tanh is the only activation function that gets used? No. So what are the other activation functions that you used in your 2-2 projects? Sigmoid, ReLU, softmax, anything else? Not much. Okay, so these are the commonly used ones. So for today's exercises or today's session, we'll stick to Tanh. Once your understanding progresses well, then we can switch to some other activation functions as well. Now let's see a visual representation of tan h, the derivative of tan h. How does it look like? So I have one link provided here. You can also visit the same link. So this is initialized with some other function. So let me write tan h of x. So this is the tan h function that I get. And now when I move this here, I can see that the line is changing. So basically, when I nudge the values on this curve slightly, it shows me in which direction am I moving. Am I moving upwards or am I moving downwards? So let's say we are stationed at 0 value, 0, 0. But I want to slightly change my x value because that is the only variable that I have in my entire function. So if I slightly increase my x value by a few points, then where do I move? So I'm moving up the graph, right? So moving slightly, adding a slight positive value to 0 was moving me towards the right. Whereas if I choose to move towards the negative side, I'm moving down. And what happens if I subsequently keep moving my x value? After a certain point, we notice no change. The slope has become 0, right? So we'll see this during vanishing gradient problems and gradient saturation. You will understand this better. When the slope becomes 0, tan h can do only so much. So what else has to be used in that case? But for now, what you can remember is a derivative of this tan h is going to give me a direction. It tells me whether the output is going to increase with increasing values or is it going to decrease. Now, right now it is increasing, decreasing, it is proportional. But after a certain value of x, it becomes saturated. It doesn't change. So it has reached the topmost value and from there it doesn't change. And so with the negative values as well. So I move down further. Now here the slope has become 0. That means no matter how much I keep changing my variables, if I make them too negative, there's not going to be any change. That means the neuron can learn only so much. So you have to play within a tiny range of values. So this shows how the weightage, the weights and biases can be changed accordingly. So you can move the weights and biases only within a certain range. Beyond that, there's not going to be any impact, no matter how much you keep adding the values or decreasing the values. So that is the main idea of derivatives, and whenever you're getting confused, you can visit the websites of this kind. You have GeoGebra, you have Desmos, which help you with the visualization. So if you are in a confusion whether to use Sigmoid or whether to use tan h or ReLU or any other function, then you can visit these websites, understand why exactly is your neural network not getting trained properly. Why is it getting overfitted or underfitting? So you can understand little bit. At a layer level, you can understand if by changing the activation functions, is your neural network performing any better? And this visualization is very essential. Otherwise, a neural network will be treated only like a black box, and you will not be able to enjoy training neural networks. So we saw a quick visual representation of tan h and how a derivative of tan h gives me the direction, how values can be changed, and if I change by a tiny bit, how is my output impacted with that? So this is a derivative of tan h function. You can also search on the internet. So if I do this, you have that quotient rule, right? D of u by d of v is equal to u dash v minus uv dash by v square. So it is using the same principle. And when you do the math completely, the derivative of a tan h function turns out to be 1 minus tan h square, right? So this is simple. And again, tan h has two different ways of representation. If you search on Wikipedia, you'll find it, or any other representation, any other website also you will find it. Can you quickly search and let me know what is the other equation for tan h? e to the power x, ex minus e power x by e power x plus e power minus x. This is one representation. There's one more. What is it? Did you find it? Acha, what is e power minus x? Is it, what is e power minus x? How can I represent it in another way? Huh. So what happens in that case? Even without Wikipedia or ChatGPT also you can tell me. No, I don't want it in sine or cos or cot, secant. No, I don't want. In exponential representation itself, what is it? Huh, yes. So again, tan h, if you search on the internet, it will have multiple different representations. E power x minus e power minus x by e power x plus e power minus x is one representation. The other representation is e power 2x minus 1 by e power 2x plus 1. And you can also re-represent it as sine by cos, right? If my memory serves right. Because it's been 10 years since I learnt mathematics. So you have to help me with that.
I have a question to the students.
Yes, sure, sir.
This is simple. I want an exact value. If x is equal to 5 and y is equal to x cube, what's the value of d of y with respect to x? dy by dx is equal to how much? Yes? How many of you say 75? Please raise your hand. How many of you say 75? How many of you say 75? Okay. So the others, those who have not raised hand, you don't know calculus. You don't know differential. How do you calculate all, right? Yes? You don't know derivatives. Yeah, please. Those who don't know, it's a chance. Today, when you go home, just look how answer is 75 exact, but how 75 has come. Okay? Please look into it. Because whatever mathematical representation what SRIPOOJA is talking about is with that respect of the formula and the rules. Please brush up your skills. Then we will revisit same in the next session. Okay? Yeah, SRIPOOJA, continue.
Yes. And also another additional question. So what is the derivative of e power kx? Okay. So you're all good with mathematics. Fine. So you can partake us. So that brings me to exercise 1 for today's session. And what is exercise 1? It is on tantric and you have to implement the derivative of tan h function. So please log into tantric. The exercise will be available in a minute. We are enabling the exercise. How many of you are not able to log in? So it's working, right? Log in.
Please confirm. How many of you are not able to see the login screen? If you are not able to see, reconnect to KMATOD and then refresh. Yes, SRIPOOJA, what is the time duration for this exercise?
5 minutes.
5 minutes?
Yes.
Okay.
Case and couple of other hidden test cases. And please make sure that you round off the values accordingly. I mentioned in the description. You can also take a look at the assertion that we have in the visible test case. Then you will know what is the expected output like. So how many of you got 100? Only a few? And what about others? So you should be able to find week 1 exercise 5. We just enabled that exercise for you all. Do you find that exercise? Week 1 exercise 5. Now we are dealing with exercise 2, which is with the sigmoid function. Whatever you did with tan h, calculated what is the output of tan h, derivative of tan h. In the second exercise, instead of tan h, you have to use sigmoid function. What is sigmoid of x and what is derivative of sigmoid with respect to x? So here's a description of the second exercise. what you can see in the notebook once you fetch it. This also requires you to do a round off. And two methods have to be implemented. The signatures are provided for you. One is for sigmoid, the other is for sigmoid derivative. np.tanh. And what about others who are not using np.tanh? Did you still get 100? You got 100? You did not use np.tanh. Okay, for those who are seeing that there are some decimal issues, few values are not matching. Out of 10, only 2 are not matching and your test case is not passing. You can try replacing your implementation with the tanh, which is provided by NumPy. Try that once. I think there is some issue with the round off. We certainly acknowledge this, and in upcoming sessions, we'll make sure that these issues don't come up. Meanwhile, you can try using NumPy tanh.
One important point, when you click on submit, don't repeatedly submit. Submit, wait till you get the feedback, view feedback link. Just wait, because if you repeatedly submit, what happens? A lot of requests will be in the queue. And second, while leaving this room, please log out. Okay? Yesterday you did not. Please ensure that these two steps are important. When you submit, wait.
So this is the third exercise. It's again on the topic of derivatives itself. Now derivatives have a different way of representation. This is also one of the ways of representing it. How much is your function changing? The rate of change of a function. And it is represented with this formula, f of x plus h minus f of x by h. So if I slightly nudge my value, slightly nudge the value of x by a small factor of h, then what will be the impact on my output function? So that is what is depicted by this equation, and you have to implement this in exercise 3. So we enabled the third exercise. It has a name day 2 exercise 1. Do you find the notebook on Tantric? Yes. Okay. So this is the description for exercise 3, where you have to implement this math function, which is mentioned in point number 1, 2x square plus 3x plus 4. You have to take x values in the range minus 5 to 5 with steps of 1. And then you have to plot a graph using the x and y values. We are not evaluating the graph part, it's only for you to visualize and see how it's working. Then you have to nudge the values of x by using the h variable. And then you have to finally calculate the output. What is the final output when we do f of x plus h minus f of x by h? It is to know the rate of change of the function. And also please note that you have to use round off, and you have to round it off to 4 decimal places.
Once I say please check your view feedback, then please check 4th, 5th and the latest one. This will not happen from the next coming forward. Only one exercise that will be stopped now. Pranay, can you just close exercise 4?
4 and 5 have been closed. Exercise 1 of day 2 will also be closed. Okay. So we closed exercise 1 of day 2. What you can now find is day 2 practice notebook. Do you see that? Day 2 practice notebook. Yes? So fetch it, keep it ready. This is not going to be graded. You can treat this like a playground or online editor. While I'm working on the code, you can also simultaneously work on the code and see how the code works. And visualization also, we can keep it handy. So for our future sessions also, we plan to do on the same, because you'll be connected to the local network. So every time switching to other network or having a Jupyter notebook will not be that easy. So we wanted to simplify this setup for you. That's the reason we have a practice notebook. And what do you find in that practice notebook? Is it empty? No, there is some code, right? So we'll see what exactly is that code. So coming to agenda of today's session, we will be visualizing the math function in the form of a node graph. Because the math functions, the 2x square plus 3x plus 4 and the neural network nodes, there is no sync at all. We are not able to draw parallels between what is happening in a math function versus what's happening in a neural network. So let's make the representation of math functions also in a node format, so that it's easy for us to understand the math processing, how the gradients flow, how the data flows, what happens in a forward propagation, what happens in a backward propagation. So that's the reason why we'll be switching to the node representation of math expressions. For that, I provided you the code to generate the graph. But there is a class which is not defined yet, right? We did not implement the methods in that class of value. So we'll be implementing that in today's session. And secondly, you will also understand how to manually calculate the gradients. We understood derivatives. It certainly has some significance in ANN training. But what is gradient? Is it completely different from derivatives? How is the gradient going to help us in tweaking weights and biases? That also we'll understand. But for today's session, we'll do it manually. Remember, we are going to do it one neuron at a time. And we'll also understand a little bit of back propagation, not in the automated mode, but in the manual mode. So you will be doing the calculation of gradients. So coming to visualization of the math functions, you have to use the practice notebook. There is a value class which is already defined, the signature is defined. The methods are not implemented yet. We'll implement them. And then there is a draw dot function, right? Draw dot function is basically going to help you with the implementation of the graph. So if you want to visualize an expression, a math expression, you can use the draw dot function. You can take a look at the draw dot function later whenever you get time. That we won't be discussing today. So what we'll discuss is the value class and we'll implement it. So this is how your math function will look like if we use value class and draw dot function correctly. Right? So this is a simple equation, C equal to A plus B. Very simple. But the representation has changed. We no longer depend on the math representations. We changed it slightly into this node graph. So we'll do that using the value class first. So allow me some time. I'll copy paste the code. So this is the code you might be seeing at your end, right? The same. I'm using a Google Colab notebook, but you can use the Jupyter notebook which is provided to you. So this is the first cell, or there might be an import libraries, but after that you see trace function, you can also see draw dot, and later there is only this defined, class value and init, but nothing else is there. Now let's go to a next cell. Now the idea is to implement C equal to A plus B, right? Using value class. And what all do I want in my value class? It should basically hold a label for the variable. It should have data. It should also know what is the operator, and it must show me the output. So we'll keep adding these elements to the class, the value class, right? So in it, what does it take? The first one will be self. Then I want this, data, right? So I will be initializing the variable using value class. I need to pass data for that. And these children, operator, label, you'll understand them. Children and operator are being used by this method, draw dot. You can take a look at it. It's basically for traversing through the graph, to generate the graph, left to right, right to left. That is exactly where it's being used. And label is coming from here, the label that we are generating here for each variable, right? So let's get started with this. So self dot data is coming from the data that I am initializing. Then self dot, what else is there? Grad. So for now, what I'll do is grad, I'll just initialize to 0 because we are not calculating the gradient yet. Just because the methods should not throw an error, I'm just initializing this to 0. Next we have self dot children, which has to be initialized to a set of children. Now this is a topological traversal that we are doing. We are using set to eliminate duplicates. You know the difference between set and a list, right? List allows duplicates, set doesn't. Then we have self operator. So this is to indicate what kind of operation is happening. And then self dot label is equal to the label that we are initializing. Now these are the default initialization that is happening. Children, by default, if you pass nothing, then it will be initialized with empty set of children. If you don't specify the operator, it is going to be an empty string. Similarly, label, if you don't specify, it's going to be an empty string as well. So now my value class has data, it has grad, it has children, OP, and a label. All right, so let me run the cell. So are we in sync up to this step? Did you implement the same steps at your end? Right? So now I ran my cell. It did not give me any error. Now the idea is to have A equal to value. Now because I'm using this value class, I don't want to go ahead with normal integer assignment or initialization. I want to use the value class. That's the reason what I'll do is value 1.0 float value, and the label that I want to specify here is A, right? Because I told you what is our goal is to have A equal to 1, which has a label A. So this is the first representation. If I run the cell and try to print A, let's see what happens. So it's giving me main value at some hexadecimal code. But don't you think this representation is, it doesn't look good, right? Can't we change it because this is not readable for us? We cannot debug the code if we have this representation. So normally these classes have a D underscore methods, double underscore methods, which are predefined. I don't know how many of you all are good with OOPS concepts in Python, because I got to know that Java you're well versed with. So in Python, they are D underscore methods. We can override them. So for changing the representation of this value class, this variable, there is a D underscore method which goes by the name REPR for representation. So what does this take? It takes self. Let's try this, and yes. So we have to return something here. Let me try this. I'm not too sure if it takes data. It should be correct. So I will use formatted strings in Python, where I give value is equal to whatever value I am initializing. So self dot data, right? So what did I do? I use this method to represent the variable differently, the value that I'm initializing, the representation I'm trying to change. So let's see if this works. Now when I rerun my cell, so it's now changing the representation. Earlier it gave me a hexadecimal value and something else which I couldn't understand. Now I modified the representation, it's giving me this, value equal to 1.0, right? So that is the initialization. Now A part is sorted.
Yeah, you saw how we do this in Python, right? We have that double underscore REPR, and it converts whatever the object is into a printable word. If I wanted to do this in Java, what would I do? Answer is toString. You have to write a toString method which produces a string. That's what I wanted to check whether you guys, because you need to, as you are seeing this class getting developed, you need to understand the equivalent Java.
Well, now we have A value initialized correctly. Now our plan is to also initialize B, right? Now let me copy paste the same cell but change it to B. B and the value is 2 because we wanted it that way, and label is also set to B and then B. Now let's print this and see what happens. So it's giving me the correct value 2.0. That's how I initialized it. Now coming to C. Now normally in Python, if we want to do this, what do? We just say C equal to A plus B and then we print C, right? C equal to A plus B and then C. So let's do this step and see what happens. So it's giving me an error, right? So it says unsupported operand types plus value and value. So it's basically complaining you're giving me plus operator with value class. I don't understand what is value class. What am I supposed to do with that value class? Because for Python, it understands integers, float, other values. But value class is something completely new because we are defining it. So we have to instruct Python to take this input and do the addition as well. And where are we supposed to do it? In the same value class. Now since we are talking about the D underscore methods, there is one more for addition, which has this method signature double underscore add double underscore. And what does this expect? How many arguments do you think it takes? 2 arguments. So one is certainly the self, and then we can name it as other because we are adding 2 different values here. One is itself plus what is preceding it or succeeding it, right? So in this case, now I will say I want to save it in a variable out, and I will do self dot data. No, this will not work. What I have to do is initialize it separately using value class. And this time, since I have to use the value class to maintain homogeneity because we are dealing with the value class type only, the typecasting is not working. So I have to return the value, the return that is A plus B, again in the format of value only because I want to do some other operations. So if I suddenly convert this into integer and I try to add another value data, it's not going to work. So to maintain homogeneity, we'll again initialize this output using value class itself. Now what does this value class expect? I have to pass.
Sigmoid, can you just zoom in a little bit? Just, yeah, thank you.
So this value class, just like how we initialized for A and how we initialized it for B, we have to do the same thing here, but slightly different because this time it is an addition, right? So I'll take the addition value itself, which is self.data, which is coming from the first variable, that is A. A has something called as data here because in the class itself we defined this. So we are doing value of self.data plus other.data, right? So basically it's going to take A, it's going to take B, it's going to add both of them and initialize a new variable output with the same value class, right? So I'm adding this, and now let me check what else is there. Data I have given, but what about children? I haven't given anything here. So what are the children in this case? If you have a plus operator, there are 2 children. If we go back to this representation, plus. So there are 2 children for this node, which is A and B. So in this case, it is self, comma, other. So I'm saying for this operator plus, let me go back to this representation, it becomes easy. For this operator plus, it has two children. And what are the two children? It is the value A as well as value B. Whichever two value variables that we are adding, they are the children for this operator. So that's how we need to initialize this. And why didn't we use children here when we were initializing A and B? Because they are independent of any children. They are unique values, right? They don't have dependency yet. That's the reason we did not pass any values to children, and they were initialized as empty set. But in the case of add operator, we have to indicate Python that it has two children, which is self and other. After this, what else do I want to pass? OP. OP also we did not use for A and B. Now we have to use the operator sign, because this plus sign, what we see here in the node, it's coming from this argument, underscore OP. So we need to initialize this as plus. All right. So label, I don't want to specify it here. I can specify it later also once the output is returned. I still have that flexibility. So I don't want to mention anything here. So I will just say return out. So let's run the cell and see how it works. So well, there's no problem in this code. Let me rerun these cells, because we made some code changes. And now when I run the third cell, it is working. So it's giving me value 3.0. So now Python is not complaining, because we indicated to Python clearly that addition is what you have to handle. And since value class is what I'm defining, I will also define how you should do the addition. So now this is done well and good. But what about the representation? We did not do that yet. So let's see what happens if we use draw dot with C. Okay, so draw dot is complaining that object has no attribute prev. And where exactly is it looking for prev? It is looking here. So I did a mistake here. Draw dot was expecting underscore prev, but I used dot children.
You saw the add. You saw a bit. Underscore, double underscore add. What is that called in classic object-oriented? How do you do that in Java? No, yes. You don't do that? Java doesn't support operator. Who supports? So operator overloading is, this is the way you do operator overloading in Python by writing add. So why does Python support and Java didn't support? C++ supports. Are you understanding my question? C++ has nice operator overloading. It came much earlier. After that came Java. Does not support operator overloading. Python brought it back to use double underscores. Why did that happen? Why did Python bring it back? I'll ask you this again tomorrow.
So in my value class, I did this fix. Instead of using self dot underscore children, I changed it to prev. And why did I do that change? It's because draw dot is using that variable. It's using that feature from the value class in order to compose this final graph. Now that I fixed the code in the value class, now I am able to generate this graph, right? So it has A, it has B, whatever I initialized, I am able to see it here. So up to this point, are you able to run the code? Do you see the graph at your end too? No? Yes or no? How many were able to run the code and you're able to see this graph? Please raise your hand. None?
Can you just show the value class?
Prev. So this is it in the value class. We don't have anything else. You must have missed 1 or 2 lines of code. That's the reason you don't see the graph. If you're facing some issues, please let us know, because this value class is what we are going to use for a couple of other sessions too. It's important. In addition, when you initialize the value class, you have to pass self and other, not self.data, other.data. It is only self and other, because you're indicating the children nodes. It's not data there. For addition, you will be using data.
Give us a minute, no problem, because that is a visual way to see, so we will resolve it, but that's independent, that doesn't depend upon your assertions, which we are going to give an exercise on, okay? Don't worry about it.
You can keep a copy of that code which has trace and draw dot method. At home, when you have internet access, you can install GraphViz and use that code. So it is basically to give you a visual cue of what is happening in a math function. So our assertions exercises won't be based on it. So assuming you all have implemented this code up to this point, let's proceed further. So a plus b, c equal to a plus b, everything is good. But what about if I introduce a new operator here? Do you think it's going to work? No. So what should we do for that? Let's say I want to introduce multiplication operation. What should I do? The same, right? Whatever I did for addition. So for the same thing, I should be doing it for multiplication as well. So let me copy paste this code, but instead of using add, this time I will be using multiplication. And instead of doing an addition here, I will be doing a multiplication, and I will change the operator. So you can see there are 2 methods now, one for addition and one for multiplication. And if you're copy pasting the code, please be careful to change all the operators correctly here. The label has to change and the operation here has to change. It's a multiplication operation. And do the same thing. Now let me initialize one more cell. I'll rerun this code. So I will take another cell, a new one. And this time what we will do is C equal to A into B. The same thing, but this time multiplication. So initialization here. And this time C is equal to A into B. And let me print C and check, verify if the multiplication is working correctly or not. Good, so let me change the values to something else, 3, and also let's try with negative values, whether the method is able to handle it or no. So -6, this is working fine. The value is correct. So if I do a draw dot, since it's not working on many machines, you can view it here. So draw dot of C, it's generating this node graph now. And gradients are all set to 0. But we can see that A and B values are here and then data is here. Now for C, it is blank, this space here. Why is it blank? That's because I did not initialize the label here. Remember, we are not initializing the label here for the output. So I can do that initialization here explicitly. I'll do C.label is equal to C. And now I can see that the output has a label C. So this is what is expected. And now that you understood how to use the value class, and I clearly gave you how you're supposed to implement it, the representation, how it has to be changed, how you can override the methods for the math operations, the basic ones, we can proceed with the next exercise, which is on Tantric. Now this time, this is slightly a tricky exercise. You have to generate a node graph for a mathematical expression. So this is exercise 4 for day 2. You have to use the same approach, the value class, draw dot method. But if draw dot is not working, still fine. We don't have any assertions on that. It is for you to view the graphs. But apart from that, the value class is very important. All the methods in that value class must work correctly.
If graphs are not working, you can just comment out the package if you're importing.
Exercise, you should be able to fetch this notebook. Now, the node graph or the expression that you have to implement is not that straightforward like we discussed in the notebook earlier. It is a little complicated because I'm using multiple operators, I'm using parentheses, and there are intermediate variables also that you have to initialize. Now, I don't want to give that hint because it will be very clear if you look at the assertion, what is needed. So make sure that the variable names are correct. Use the same name for all the variables. Otherwise, the assertions will fail. And labels also we are checking if you are initializing them correctly or not. So initialize the labels correctly. So the heart of this program is the value class. If you implement that correctly, other things will fall in place.
No one? Okay. So I think this will be the last exercise. Please submit before you leave.
So this mathematical expression is clearly defined here. If you have implemented everything correctly in the value class, one place where you might face issues is here, because we are using some additional variables too, that is E, F, to store the subset of that math expression. So you have to understand that. My hunch is maybe your test cases are failing there. But if there is some other issue, then it could be probably with the value class implementation only. You have to correct it. If you think value class is implemented correctly, everything is correct, but still your assertions are not passing, then it is maybe because of those intermediate variables, E, F. So take a look at that, you will understand.
You will
I
be
show it.
facing
Try it now.
another tool called as Prashn Manch.
It could be the same thing what he
This
did.
Friday.
No
So,
argument?
in inter-process communication, shared memory, message queue, and semaphores. So this is the topic. Please prepare and just interact with our Prashna Manch. Let us see how is your matrix. So not only theory, code, you will be asked to write code also. Okay? Just prepare on these three topics on Friday. Let us see. Okay? The coding will be not simple coding. Basically, you need to debug. Jumble. The code will be jumbled. You need to assemble properly. Got it? So, prepare in that way. Let us see how many of you clear it. If you want a clue, I want SRIPOOJA to explain.
I part everything is correct. Most of you are struggling with the labels. So that is my assumption. So once you create those intermediate variables, once you initialize them, then you can initialize the label as well. You can try that approach. But besides that, if you're facing any issue, please let us know, because this is important for our next sessions.